thank you very much. And a special thanks to the organizers for having me at this wonderful conference. I'm very happy to be here. And I want to talk to you about the topic that has been occupying most of my research for the past 2 years. It's a very fundamental topic, I think. And yes, so it will be about non-stationary quantum many-body dynamics. Let me give you an outline of my talk. So first I will introduce what I mean by non-stationarity. Basically, I mean complex long-time dynamics. I will contrast this with standard statistical mechanics behavior, where you see equilibration to stationarity. Then I will introduce a concept I call dynamical symmetries, both in closed and open quantum systems. So I couldn't help myself. I put 4 examples, one of which is completely closed, the other one functions as both closed and open. And even though the topic of this conference is dissipative systems, I do this because they are all prototypical in a way, and the closed system examples help us understand the open ones better. Yes, so, and then finally I will conclude. Okay, so what is non-stationarity? Well, by that I mean that we have some local quantity that is long time dependent, namely something like particle number, heat, charge, and so on, that changes in time for a very, very long time compared to the characteristic timescales of the system. However, statistical mechanics teaches us if we have a many-body system and lots of interactions, then we will generally expect that the system will equilibrate to some stationary value, that is time-independent state, where these local observables are no longer changing time. Now, the crucial question is, okay, so what is this time scale that happens for a non-equilibrium system? And indeed, this has been studied a lot in recent decades, both in closed and open systems, closed many-body systems, where a big system can function effectively as its own bat for its local degrees of freedom. And it turns out that statistical mechanics in most cases works quite well. All local observables tend to relax to stationary values. Importantly, they do that quite quickly. So they all, as far as I know, all the standard cases have relaxation at orders of magnitude the same as the characteristic timescales. And they relax to time-independent states, usually thermal equilibrium states, but in the case of open systems where you can have bats at different chemical potentials, for instance, they can relax to non-equilibrium stationary states. However, these states support current, but they are still time independent. Okay, so now what do we see in the real world? Well, in the real world, both say temperature variations throughout the year, in biophysics, even in financial markets, really all over the world around us, we see non-stationarity. So things that cannot be described by time-independent probability distributions. Now, this is puzzling in a way, because these systems are non-stationary for extremely long timescales compared to the microscopic timescales of these quantum many-body systems around us. So this is a bit puzzling if you think about it. Indeed, something like this has been already hidden by Anderson in his seminal essay on symmetry breaking and complexity, More is Different, where he says basically that one type of complexity is ordering or regularity in the time domain, which is remarkably common. He does not comment much more on this, but the point of his essay is that one cannot really understand complexity from the microscopic fundamental laws. However, I would like to understand the emergence of periodic time dynamics as a precursor to more complex dynamics on a fundamental quantum level, so from the microscopic principles. So let us begin with a simple naive approach. I have a system of some large number of interacting particles. I can, in principle, I hope you see my cursor, I can, in principle, diagonalize the Hamiltonian, find its eigenfrequencies, and formally solve time evolution for some generic observable and generic initial state. Now, since the initial state is generic, I assume that there is no special structure. It will excite a microscopic number of eigenmodes, in principle, of our closed many-body system. The eigenfrequencies are random, more or less. There's a continuous spectrum, but there is no special structure in them generically. And what we find, what we're basically doing in this sum is summing a bunch of infinite waves with random frequency and phase. And this causes something called eigenstate dephasing, or basically it's a form of destructive interference. And then in the long time limit, this observable goes to a constant value that does not change in time, its expectation value, in accordance with statistical mechanics. Okay, so this is the most simple, this is the most generic case we can expect. However, let us look at how we can avoid this. So I have plotted here the eigenspectrum. I have absorbed the I in omega into lambda j. I did this because I will connect with open systems later. So this is our spectrum. It's dense and incommensurate. But let's say there's a large number of frequencies. It's not completely random. Let's say there's a large number of frequencies that are the same. Call them omega. I claim that the condition for the appearance of such large number of frequencies is this algebraic structure that I call a dynamical symmetry, which is like, as you can see, a type of spectrum generating algebra, but satisfying properties of extensivity and locality. I don't want to be too technical here, but the point is, basically, this dynamical symmetry needs to be something that has non-zero overlap with local measurable observables. Then I can invoke maximum entropy principle, and you can basically argue that in the long time limit, much like in standard statistical mechanics, the system will not relax, but will go into something that's like a thermal state, but with an oscillatory chemical potential dictated by this A. And operators that have overlap with A, in the long time limit will oscillate forever. Okay, that's the case for the closed many-body system. I'm now moving to open systems. Okay, so I have my closed system at first. It has, again, a dense and incommensurate number of eigenfrequencies that are purely imaginary because it's closed. I absorb the I, remember, in the lambda. And now I open it by adding Markovian noise to it as effectively the Lindblad master equation. This, you can think of it as coupling to some environment, but I'm sure that almost everyone at the conference is familiar with this. Then what happens is that these purely imaginary eigenmodes turn into decay modes. They acquire negative real part and they start to decay. We are left with one stationary state that's exactly zero always, but we can also have purely imaginary eigenvalues, which will correspond to persistent oscillations. Yes, now these purely imaginary eigenvalues are, I emphasize that these are not necessarily pure states. They can be more general structures, but I give the necessary with the caveat, and I'm happy to discuss this later, and sufficient condition for the existence of these purely imaginary eigenvalues. And basically, it's like our dynamical symmetry from before. However, now we demand that the dynamical symmetry also commutes with the Lindblad jump operators. And in that case, you will have purely imaginary eigenvalue. Okay, now I will move on to examples. So my first example is really a closed many-body system. I will go quickly through it simply to give you a picture of what happens. So it's the Heisenberg XXZ spin chain. It's an integrable model, one dimension, the standard model of quantum magnetism. And you can show using beta answers that it indeed does have operators that are quite complicated. They are quasi-local, but these operators are dynamical symmetries. For instance, I'm not going to give you what the operators look like, but for instance, for the case of delta minus 1/2, they are these three-side terms, and you have higher operator terms in this sum, basically up to infinity, but it's still extensive. Now, the eigenfrequency of the frequency omega is a nowhere continuous function of the interaction straight delta. Remember, I forgot to mention that this is the anisotropy. So the XXZ chain has different coupling in the ZZ direction. And it's a nowhere continuous function of this anisotropy. Remarkably, we get a fractal dependency on delta of the period of the persistent oscillations. And indeed, now any operator that has overlap with Y will persistently oscillate. We can check this. We can actually compute analytically the amplitude of these persistent oscillations, but we can compare it with numerics. So for instance, if you look at this for delta minus 1/2, this 3-site operator, it persistently oscillates following a quench. However, if we look at this 1-site operator, so just the field in the x direction, it relaxes in accordance with standard statistical mechanics. Okay, now my other example is both closed and open, and it connects to something we discussed yesterday on the panel about stability to local perturbation, which I think some of you may find interesting. Okay, so now what do? I take 7 qubits. I arrange them into this geometry. With these interactions between these qubits are arbitrary. However, the only thing I demand is that the interactions are such that you have an axis of symmetry going from 1, 4 to 7. Yeah. It can be shown that if this is true, then there is a dynamical symmetry, again, now one that is strictly local. So by that I mean it only lives on these 5 sites in the middle. It does not, it is an identity, it is trivial, it is completely localized on these 5 sites. It's an identity on site 1 and 7. And now this has, the fact that it's an identity has important implications physically. Among other things, it means that we can take our 7-qubit system and couple it on these 2 sites where the dynamical symmetry is an identity to any other system, while retaining the dynamical symmetry as illustrated here by my cat. So we can couple it to anything and the dynamical symmetry will remain here. So what is this dynamical symmetry? Well, it's something like a qubit dressed by singlet projectors. It is, yeah, I can discuss what the meaning of that is later. But anyway, so what can we do with our 7-site qubit? Well, we can couple it repeatedly to itself. For simplicity, I have removed these 2 connections. And then we get this quasi-1D structure that is similar to azurite. And it turns out that if we do that, each of these 5 sites hosts such a strictly local dynamical symmetry, but more appear that are independent of the original one. Actually, a super extensive number of them appear. Remarkably, what's quite interesting for me, at least, is this is completely stable to any local perturbation, including dissipative one. So if I add some local perturbation on any one of these plaquettes, I will destroy the dynamical symmetry there, provided I do slightly non-local type of perturbation that breaks the reflection symmetry. But all the other ones will still remain there. So this is the dynamical symmetries of this spin-laced model that is similar to azurite are very difficult to get rid of. It's impossible basically by local perturbation. So what is the physics of this model? Well, remember, observables that have overlap with dynamical symmetries will oscillate persistently forever. In particular, we see the frequency given by this most local of the dynamical symmetries, but we also see other frequencies appearing. If we do say something like linear response at infinite temperature or any other temperature, infinite temperature as an example, and initialize to various values in the phase space, we see that we are allowed a system to evolve, and say the total spins in the x and y direction will go into something that's like an attractor. So they will go into this attractive basin and display complex dynamics at these frequencies. So remarkably, we get something like nonlinear dynamics, even though our system is fully linear. There is no external environment. There is no source of nonlinearity. Indeed, this is one plaquette. This is just completely finite dimension. And we see emergence of something that is associated with complex dynamics. Now I will move on to finally to really open many-body examples. And my first example is actually the one that led me to discover these whole structures of dynamical symmetries. And it's a very simple example, but it's not completely simple. So you will see that this has some interesting physics as well. Okay, so what do? I take fermions with spin, I put them in an optical lattice. Well, I don't, but I imagine I do. And then I will model this by a d-dimensional Hubbard model, Fermi-Hubbard model. You have hopping between the nearest neighbor sites. You have on-site interaction. You have, I will allow for distorted chemical potentials to be more interesting, and I have a magnetic field. Now, it is well known, the Hubbard model has 2 S2 symmetries. by adding a external magnetic field, we have promoted the spin symmetry, the spin SU2 symmetry, to a dynamical symmetry, basically trivially. So, okay, so you see what now this relation holds for the total spin raising operator. You may say, okay, this is this is like spin precession. Yes and no. There are subtleties because of the disordered interaction. Basically, what is the interesting thing here is that if I add dephasing, so for instance, I immerse my optical lattice in a BC, and dephasing is just in the charge sector, so that commutes with the S plus. So this satisfies the conditions I gave before for a dynamical symmetry in an open system. And then what happens? Okay, so let's look at the physics. So I take my system and I initialize it in some quench protocol, and I allow it to evolve with time. Now, the blue curve represents the fully closed system without any external source of noise. As you can see, it's basically just random noise, the expectation value of some local on-site observable. Whereas the open system, that is the one that has an external source of noise given by the Lindblad, is nice and oscillatory. So for me, this is quite counterintuitive. But what has happened here is that the dissipation has selected only some of the frequencies dictated by the relatively simple just relatively simple spin raising dynamical symmetry. But because of the disordered interaction, the closed system has lots of frequencies, okay, that kind of destructively interfere into this noisy pattern. Okay, my final example, and this is related to the bias's great talk from earlier. It is precisely the experiment they did. So it is the spinor BC in a very lossy optical cavity that you have these two density and spin modes. And what they see in their experiment from here is that they find that in the large loss cavity limit, they find persistent oscillations, so long time oscillations, even without any external driving, time-dependent driving. Okay, so we can understand we can get these oscillations using this construction, but there is it's a bit subtle, but you can do it. The point is, we model these two component BCs as two plus and minus spin mode, spin raising operators, collective spin operators. And we include cavity loss in a Lindblad type form. Now, this model is very related to the decay model. The decay model is just lambda S0, okay? But this is different from the decay model. If we go beyond mean field theory by using, I'm not going to go into the details, but basically you do a strong perturbation theory in large kappa, so large cavity loss, which is appropriate for the cavity they use. And in the first order, you immediately find purely imaginary eigenvalues. Well, beyond the zeroth order. The first order, you find purely imaginary eigenvalues that are equally spaced, quite frequencies that are quite close to the ones they see in an experiment. Now, this is a type of quantum xenodynamics, if you will. So why did we do this perturbation theory? Why did we go beyond mean field theory? I emphasize that mean field theory can also capture these oscillations. Well, this allows us to access the higher order correlators. And indeed, we see that they oscillate as well. More specifically, we find spin squeezing in the y direction, which also oscillates, which is interesting and potentially important for quantum metrology. I will now conclude. So the goal of my research is to understand the emergence of complex dynamics from the fundamental quantum laws. I hope I have at least convinced you that this is an interesting question. If I have done that, I further hope that I have convinced you that dynamical symmetries are very important for understanding this. I gave you several physical examples. There are many open questions. There is also there is some relation with other forms of non-stationarity, such as quantum scars and time crystals that I couldn't talk about. And yeah, lots of other work that we have done that I also couldn't talk about. But yes, that's it. I'm done. Thank you for your attention.
Thank you, Berislav, for the impressive talk and impressive also how you kept the time. There is now room for some questions. And I would start then. So my first question is, so I find it very nice how you point out how the use of a Liouvillean selects, say, one frequency and practically damps down all other resonances. And I was wondering, so the excitation of all other frequencies, I was wondering whether you can engineer it, so whether you can tailor in a targeted way this behavior.
Yes, so one would ideally like to have a BC that, to achieve this example, to have a BC that does not, that interacts spin agnostically with the fermionic atoms. That can be accomplished, say, depends of course on the type of, in these types of Bose-Fermi mixtures perhaps, but it will depend on the finding the correct Feshbach resonances so that the interaction is spin agnostic. And indeed, I believe that this is within reach of, possibly within reach of current cold atom experiments.